So I'm talking about Mount Wilson Observatory, and my voice may lag a little bit because internet connections being what they are. I'll start with my only commercial of the night. We've had basically zero operational income because of the pandemic and the fire. And now the roads are closed to the observatory. So if you want to learn more about the observatory, there's the URL. Go and visit. If you want to donate to the observatory, we'll be happy to allow you to do that. And that's the end of my commercial. I'm going to talk about, assuming my slides advance, which they're not doing at the moment. There we go. I want to talk about the founding fathers of the observatory. I just want to mention that everything that happens because people make decisions to do things. And the two key players in the foundation of Mount Wilson Observatory and modern cosmology, astrophysics, and everything else are Andrew Carnegie and his money, and George Ellery Hale and his brains and personality. Carnegie was dirt poor when he came to America, became the richest man in the world, was a ruthless businessman, nasty character. But when he got old, he decided to give away all of his money. And one of the things he gave his money away to was through the Carnegie Institution was Mount Wilson Observatory. A lot of money. And it was one of the first examples of really industrial level science was Carnegie's funding of Mount Wilson Observatory. And George Ellery Hale, who was a physicist, got his degrees at MIT, became interested in astrophysics and especially the question of stellar evolution and the sun. His real interest was in observing the sun. And he is seen here in this picture in the 150 or in the 60-foot solar tower, pardon me. His brains and his driving personality, coupled with Carnegie's money, are responsible for Mount Wilson Observatory and its entire legacy. And I'll point out that I'm used to doing these talks in front of a live audience, which is a little different than doing them online. But since the talk is being recorded, I assume,
yes,
then you'll be able to go back and see the slides and read all the text and all that good stuff. And if you need to, you can always get in touch with me through Steve or through the observatory, one way or another. I'm not that hard to find. And all you Palomar people know who I am anyway. And so I want to start with technology, because science and technology are really inseparable. And while we talk about the cosmology and the science of Mount Wilson Observatory, really the observatory was fantastically important in developing the technology of modern astronomy. And one of those key technologies, obviously, is telescopes. That's what astronomers use. And so telescopes are a big deal. And really big changes made to the astronomical telescope at Mount Wilson Observatory. As you probably know, as the beginning of the 20th century, late 19th century, professional astronomy was dominated by refracting telescopes with big magnifying glass lenses at the front end of the tube. And George Hale knew that he needed to switch to reflecting telescopes. So the 40-inch refractor at Yerkes saw first light in October, I think it was, of 1897, late in 1897. But in February, George Hale published a paper in the Astrophysical Journal explaining why you need to switch from refractors to reflectors. These are the points he made. Basically, the reflectors cost a lot less, but he needed to do spectroscopy, and he knew that. And because of chromatic aberration at Yerkes, you have to photograph each spectral line individually, which is a real pain, whereas you can get the whole spectrum with a reflector. And he wanted to do infrared astronomy, and the glass in a refracting lens is opaque to infrared. So you need to get rid of the glass in order to be able to see the infrared at all, those wavelengths that get through the atmosphere anyway. And so for a number of reasons, he already knew he wanted to switch to a reflector, and that reflector was the 60-inch telescope, which I'll talk about in just a minute. But George Richie got that job. So George Richie was teaching manual arts in Chicago when Hale found him and recognized his talent and brought him to Yerkes Observatory. And the picture here is what Richie called his 2-foot telescope. It's a 24-inch reflector in which he refined his techniques for grinding and polishing the mirrors. And it's basically a prototype for the 60-inch telescope. The idea of an interchangeable secondary mirror, for instance, he did that on this telescope. The idea of designing a telescope so you could do photography, he did that with this telescope. So this is a prototype for the 60-inch telescope. And so here's the 60-inch, which went online in 1908. There's a picture of it in 1910 and a picture of it the way it looks today. And I don't remember who took the picture I labeled as a Mount Wilson Observatory image. One of our docents or session directors or telescope operators took this picture, and I can't remember who it was. In the 1910 picture, that big thing sticking out of the Cassegrain focus of the telescope in the lower right is a spectroscope or spectrometer. This telescope was a major innovation, and I'm going to explain how and why by comparing it with previous telescopes. The largest telescope in the world, for instance, the late 1900s, was a 72-inch speculum metal mirror Leviathan of Parsonstown. But you can tell just by looking at the mount, this is clearly not a real professional modern research telescope. You can only look at the meridian and maybe an hour on either side of it. It's a big aperture, but it's a speculum metal mirror. So in fact, the telescope really doesn't get noticeably more light than the 60-inch does because the low reflectivity is speculum metal compared to silver on glass. So astronomically, optically, they're pretty similar, except that the Leviathan is long focal ratio Newtonian, and of course it doesn't have any other configurations available to it. It's an old telescope, and we can kind of skip that. A more realistic comparison is with the Great Melbourne Telescope. Now, it's common practice, everybody talks about the 40-inch refractor Yerkes being the largest telescope in the world prior to the 60-inch, but that's not true. The 48-inch GMT of its day was the largest in the world. And you can see it's here on, now it's on an equatorial mount. You can see the counterweight at the bottom. But the GMT suffered from not having much of a budget. So the mount that you see is not sufficient to handle the weight of the telescope. So it vibrates and it's open to the wind. When the wind blows, it vibrates. It was not designed for photography. It's a long focal ratio Cassegrain telescope. And so you can't do wide field imaging or anything like that. It was designed to look through the eyepiece at the bottom end of the telescope and make drawings. It wasn't designed to do photography. So it had a lot of problems, the low reflectivity of speculum and really the mount being insufficient. So George Richie complained that this telescope set astronomy back 50 years because this one really is the one that convinced people that reflectors just aren't going to work and professional astronomers need to stick to refractors. And of course, you want to compare it to the telescope it's planning. Since the 48-inch GMT had so many problems, really professional astronomers flocked to the 40-inch, which undoubtedly got more light into it than the 48-inch because of the low reflectivity of the speculum metal. This was the telescope that dominated professional astronomy. And as Hale noted in his paper, it's a refractor, so you can't look in the infrared. You have to photograph each spectral line individually. And because it's so long, it's an F19, so it's a 62-foot long tube, you need a really big dome to house it. Whereas the F5 primary on the 60-inch, it's less than half the size, the length. So you can house it in a much cheaper building, cheaper because it's much smaller. And it's an innovation not seen on any other telescope prior to George Ritchie's 2-foot prototype, that you can swap out the front end of the telescope and with it the secondary mirror. So it's really 4 telescopes in one. It's a prime focus, Cassegrain, Newtonian, and Coude. which made it very versatile. It's like having 4 telescopes instead of just having one. And nobody had ever done that before. That was a major innovation. George Richie figured out how to finally get a smooth, good glass image. Andrew Common made a 60-inch mirror in the late 1800s, but it was no good and you could never use it. And of course, the mount, unlike the 48-inch GMT, the mount for the 60-inch is hefty and can handle the telescope. It has a very smooth, well-designed drive. This is the telescope that proved that reflecting telescopes are good and professional astronomers can use them. And this was the transition point. All the big telescopes that followed are reflecting telescopes, and they grew in aperture fairly quickly. This is the first photograph in positive and negative taken through the 60-inch by George Richie, Christmas Eve night in 1908. Richie was kind of an artist. He wanted to make really great images, and I think he was a little jealous of turning over the telescope to scientists so they could actually do science with it. But he had to, but he was a really, really good astrophotographer. And this is a very small, like 4 or 3 by 5 inch plate. I can't remember the exact size, but it's basically index card size glass plate with a photographic emulsion on it, which has tremendous detail. You can blow up that little image into a wall-size poster and be impressed by the detail in it. Far more than you could ever get by drawing, which is how people archive their data mostly prior to Mount Wilson. But the telescope was not made to put light into an eyepiece the size of your eye. It was made to distribute the light onto a photographic plate. So you need a special custom built eyepiece if you want to actually look through it with your eyeball. And so Mount Wilson was the first observatory designed and built from scratch to archive all of its data photographically. And that's another technological achievement besides the telescope. Archiving data photographically was a huge advance. This is the 100-inch telescope, picture from 1917, which is really a scaled up copy of the 60-inch. It uses this bigger English oak mount because it's so much heavier than the 60-inch. You don't want to support the weight on a single point. But it has the same focal ratios, f5 primary, f16 Cassegrain, f30 Coude. And this is because instruments that are sensitive to focal ratio, like spectrometers, you can move back and forth between the 60-inch and the 100-inch and use them on either one. And likewise, here's the Hale telescope, the 200-inch at Palomar. I think Scott Cardell actually took this picture. I took it off the Palomar Caltech webpage. But I think Scott told me once that he took it back in the day when he was handling public outreach for the 200-inch. The primary has a slightly shorter focal ratio because it's so big. Eventually, even if it's f5, you make it big enough, it sticks out the dome like the cartoon telescopes do. And you don't want to do that. So you have to shrink a little bit so you can afford to put it in something. But the Cassegrain and Coude focal ratios are, again, the same as the 60-inch, same as the 100-inch. So you can move focal ratio sensitive instruments amongst them all. And of course, George Ellery Hale was basically the founding father of Palomar Observatory as well. So these 3 telescopes, both the 100-inch and the 200-inch, are just direct descendants of the 60-inch. And basically, every large astronomical telescope in the world today is a descendant of the 60-inch telescope. So it started the ball rolling on reflecting telescopes in astronomy. And it's the reason why all the big telescopes are reflectors. It was the very first. It was the one that started the ball rolling. Now, modern astronomy has a lot to do with astrophysics, and I want to talk about the physics end of the astrophysics. And to do that, this guy nobody's ever heard of before, Arthur Scott King, was the head of the physics laboratory for Mount Wilson Observatory. The big laboratory was down at Carnegie Observatories on Santa Barbara Street. He was a spectroscopist. He studied spectroscopy in Germany. He was a great for attention to detail. And while his laboratory spectroscopy is responsible for supporting spectroscopic work at the telescopes. It's a physics laboratory and they do physics. And while he was working with Raymond Burge at UC Berkeley, while they were doing other things, they kind of tripped over carbon-13. So if you're into nuclear physics, isotope 13 of carbon was discovered in the Mount Wilson Observatory spectroscopic laboratory. There was a problem with the spectrum, and they finally figured out it's because there's a heavier version of the nucleus hanging around. Here's a picture of what the physics laboratory looked like down at Carnegie. There's magnets here for studying Zeeman splitting. There's even some glass things like a chemistry laboratory. There's all kinds of stuff in here, and I'm not altogether sure what all of it is. But the star of the show really is this, which is a high temperature oven that got a maximum temperature over 5,000 degrees Fahrenheit, just over 3,000 degrees centigrade. Prior to this, astronomers used spark generating equipment and electric arcs in order to simulate high temperatures, and looked at the spectrum of the arc or the spectrum of the spark. And you see this all over early astrophysics papers, the comparing with the spark and the arc. But they were worried about, does electric current flowing change the spectrum in some way? This is the very first high temperature oven for supporting this kind of research, and came in very handy for spectroscopic research later at the observatory. Now, the first things I want to talk about are the famous things that Mount Wilson Observatory is well known for. Shapley's work with the Milky Way galaxy, and especially Hubble's discovery of other galaxies and the rest of the universe. Basically, at the beginning of the 20th century, people knew how far away 60 stars were, as in 60, by trigonometric parallax. So that small family of nearby stars, and everything else was just guesswork. The Milky Way is a naked eye object. You can go out in a dark night sky and you can see it. It's no problem. So discovering it sounds like kind of a pretentious title, because everybody, cavemen, could see it, but nobody knew what they were looking at. And in fact, until Harlow Shapley came along, he joined the staff in 1914 and went to work studying the Milky Way, nobody really knew what they were looking at. They had to make guesses. It was almost a philosophical discussion what that band of stars in the sky was. It wasn't really nailed down until Shapley. Now, Shapley used, as one of our listeners mentioned, the period-luminosity relationship that was discovered by Henrietta Swan Leavitt at Harvard College Observatory between 1908 and 1912. She had noticed that there was a direct correlation between the brightness and the period of variability for Cepheid class variable stars. But she didn't know how far away they were. So she discovered the period luminosity relationship, but could not key that to a distance. It was Einar Hertzsprung who did that in 1913 using statistical parallax methods. And so right away in 1914, Shapley started using this brand new method for getting distances to globular clusters, and he used other like class O stars and a few other methods to finally map out the size and shape of the Milky Way. Now, there's a number of things he got wrong by modern standards, but they were in no position to know that before. He didn't know that the dark clouds, dark spots he saw were clouds of dust. He thought it was a zone of avoidance, as he called it, where some strange thing prevented star clusters from forming. But he was the first to lay out the schematic plan for the Milky Way galaxy. And ever since then, astronomers have still been working on the problem of figuring out how big it is and what shape it really has. So I just want to bring you up to date. This is what we think the Milky Way looks like now. Shapley's picture was a lot simpler than this. There's a huge amount on this plot that he would have been unable to see. But now using radio and infrared and a lot of other methods, we can draw out a much more detailed schematic map of the galaxy. We know it's a barred spiral, and we know that the bar is binary. There's a couple of different bars, a recent discovery from the European Southern Observatory. The standard explanation for how far across the galaxy is diameter about 100,000 light years. Recent years, though, observing far away disk stars implies that our galaxy is probably about 200,000 light years across. But basically, it looks like this, and it's an ongoing tale. The project that Shapley started in 1914 is still going on today, and still people are still working on trying to figure out what it really is. Just we know a lot more than he did, but we also don't know a lot, and so there's plenty more to do. Likewise, as the Milky Way is a naked eye object, parts of the universe are M31, Spiral Nebula Andromeda, certainly is a naked eye object in a dark sky. And in telescopes, of course, people have been looking at the universe since telescopes began. But again, they didn't know what they were looking at. And it was Edwin Hubble who discovered the universe using the 100-inch telescope at Mount Wilson. So this image on the lower left here is a plate he took with a 100-inch telescope in 1923. He was looking at M31, Spiral Nebula Andromeda. He was identifying what he thought were novae, but he discovered eventually that one of them was actually a variable star. And that's his real holy grail. What he was looking for were those Cepheid class variable stars Henrietta Swan Leavitt had looked at. So he could do what Shapley did at distances. And when he finally found one, he got really excited and put a big red VAR on there. And I've got my variable star. And then he went on to discover a lot more. So he published his 3 papers in 1925, 26, and 29. NGC 6822, he published first, and I think he did it because most astronomers already thought it was an extragalactic stellar system. And so he's basically telling people what they thought they already knew. And that's a very handy thing to do when you're going to break out on this kind of new research, because if people start complaining about your methods, if they don't like your later results, you just go back to the first paper. You didn't complain back then. What's the problem? And then he looked at M33. The distances I'm giving on this slide, the first distance is the one Hubble gave in his paper, which was fantastically far away by the standards of the day. And the second one is what we think now. We know the distances to M31 and NGC 6822 very well. M33 remains an enigma. Different methods give different distances, and really nobody knows how far away M30. They're still pounding on that one, trying to figure out what its real distance is. But what Hubble did was to prove that the Milky Way galaxy, as described by Shapley, is not the entire universe. There's another universe outside, and it was really big. Nearly 1 million light years away was fantastic by the standards of the day. Now we know that it's 2.5 million light years away, and that's hardly any farther away than next door, or even closer than that. That's the hedge outside the window. The universe is a lot bigger than that. We now know Hubble also discovered the redshift distance relationship, which is the observational basis of Big Bang cosmology that was first theoretically described by Georges Lemaitre and Alexander Friedman. So, but the observations came from Hubble and made Einstein happy, because it meant that his theoretical intuition that the universe should be expanding was verified. So in his plot here, you see there's the horizontal axis is distance in parsecs, and the vertical axis is velocity, relative velocity. But all those relative velocities or spectroscopic redshifts came from Vesto Slipher at Lowell Observatory. And Hubble forgot to tell anybody that he was using Schleifer's data when he published the plot. And that's a big no-no. And he got into some trouble for that later on. But he got the distances and he used Schleifer's redshifts. Well, Shapley and Hubble, one of the reasons their distances are different from the ones we ascribe today is they were using what turns out to be the first but wrong period-luminosity relationship. Walter Baade, using the 100-inch telescope and the 200-inch telescope, figured out that there were more than one type of Cepheid variable. And this came up when I gave my talk on Monday at for the Temecula astronomers, that he published his paper in 1956. And one of the Palomar docents, I think it was Curtis, remembered a paper from 1952. Well, it wasn't a paper. In 1952, he announced what he was doing as like a preliminary result to a meeting of the IAU in Rome, but he didn't formally publish it until 1956. So he split the period luminosity relationship into two for the two different classes and instantly doubled the size and age of the universe in doing that, which was really good for Big Bang cosmology, because prior to Baade, everybody thought that the oldest stars in the universe were older than the universe, which is not a good selling point for your cosmology if you're trying to convince people you know what you're talking about. But once the universe got older than its oldest stars, that made everything work out again. And that's the beginning of the fading of steady state cosmology and the proceeding of Big Bang cosmology. So it was Hubble who first described the redshift distance relationship using Schleifer's redshifts. And once Hubble did that, then Milton Humason went to work spectroscopically studying expanding the redshift distance relationship using the 100-inch telescope, mostly at Mount Wilson. And then after Hubble passed away, his graduate student and protege, Alan Sandage from Carnegie Observatories, mostly using the 200-inch telescope, really made the period, the distance redshift relationship a landmark of modern cosmology using mostly the 200-inch telescope in Palomar. So there's a bond between Mount Wilson and Palomar where a lot of the early astronomers used both telescopes. And in fact, the two observatories of Mount Wilson and Palomar were run jointly as a single organization from 1949 till about 1972. So it's not uncommon for people to use both telescopes. And this is where we stand today. That job task started by Hubble goes on today. If you look on the plot on the left, it's the same kind of thing, velocity versus distance. The lower left little square down by the 0 zeros, the first hatch marks, that covers Hubble's original plot. You see it remains linear all the way out to 50 megaparsecs. The plot on the right isn't looking at velocities, it's looking at another cosmological variable, basically magnitude for a distance. Don't worry about that, just skip it. The important thing is that the blue lines give you theoretical curves and the red points give you observations. And you see the observations line up with that top blue curve, which is where the accelerating expansion of the universe idea comes from, rather than an idea that the people at Hubble's time would have had, which would be the dotted line on the bottom, is completely ruled out by the data. And so the story of an expanding universe accelerating its expansion is the ongoing story of the task started by Hubble, just as we're still trying to figure out what the Milky Way galaxy is following Shapley. We're still trying to figure out what the universe is following Hubble. That's not something that just ended when they stopped working. It's an ongoing project. They not only started the basic science, they started projects that people are still working on today because they're big, important questions. Now, I'm going to switch gears a little bit. Mount Wilson Observatory started out as a solar observatory. In fact, its name was originally Mount Wilson Solar Observatory, and was that until 1917, when the 100-inch telescope went online. Hale's personal interest was in observing the sun, and in fact, very important discoveries were made about the physics of the sun, and through the sun, the physics of stars. And I want to look at that, the discoveries to come out of Mount Wilson Solar Observatory. Here are the solar telescopes circa 1910. The horizontal SNO solar telescope came up in 1904, started working in 1905. In 1910, the 60-foot tower didn't have a dome yet. That came on later. The 150-foot tower is in the background. These were the world's largest and most capable solar telescopes from 1904 until 1962. So throughout the entire first half of the 20th century, solar astronomy, was dominant at Mount Wilson Observatory, dominated by Mount Wilson Observatory. This was also the SNO solar telescope, was the world's very first permanently mounted solar telescope. Prior to Mount Wilson Observatory, solar astronomers generally studied the sun only when the moon got in the way and you couldn't see it. Then they would study it so they could see the corona. But there was nobody really had a consistent program of looking at the sun itself to figure out what it was and what it was doing. That was started at Mount Wilson Observatory. And so these were the first permanently mounted solar telescopes. And this was the first permanent program of let's stare at the sun and find out what it is and what it's actually doing. Nobody had ever done that before. This was a new thing. And so the first thing to look at is sunspots. And I put this here because it tells you how radically different people saw things then than we do now. Why are sunspots dark? Well, you might intuitively think it's because they're cooler. Some people thought it was because they were dark clouds. But a big reason at the time, something that a lot of people ascribed to, was that sunspots were darker because they were hotter, not because they were cooler than the rest of the sun. And if you know how thermal emission works, that sounds completely silly, but it never worked. If you read the summary that Wilson published here in 1905, he thinks that the bright photosphere of the sun is made of clouds of solid particles, which modern astronomers and physicists would think is completely ridiculous. But in 1905, they had no way of knowing it was completely ridiculous. Solid particles, hot, emit very efficiently. But if you pound them apart, if you heat them up even more and pound them into a gas that's optically thin, now thermal emission is a lot less efficient, and they will look darker just because they don't radiate as efficiently. And so one of the ongoing reasons, a popular reason for believing sunspots were dark was because they were hotter than the rest of the sun, which is counterintuitive by modern standards. But Hale was doing astrophysics. He had a physics laboratory. He started this before they had the oven, so he's looking at the sparks and the arcs, like I had mentioned before, looking at the spectra and realizing that the shape of the spectral lines in detail implied to him that the sunspots must be cooler because of the spectral line shape. And just as this paper was going into publication, he added a quick note at the bottom, oh, we have this new oven and we're going to do some more work and try to figure out what's really going on. And by next year, they had done enough laboratory spectroscopy, especially looking at titanium and the shape of the titanium lines, that in 1907, Hale and Adams were able to nail down the fact that sunspots were cooler because they were darker because they were cooler, I should say. Well, that's an important result, but what really makes this interesting and important is this is a very early example of how real astrophysics works. They have a physics laboratory and they're doing work in the laboratory and comparing their laboratory physics to their astronomical observations. And this is a very early and one of the first examples of people actually doing that, comparing laboratory physics to stellar observations. And in 1930, Pettit and Nicholson, who had by this time started a program of infrared astronomy, which I'll talk about later, they looked at sunspots in like the up to 2.2 micron wavelength, and using thermal infrared, they were able to derive temperatures. They were using a thermocouple to make their measurements, and so their sunspot temperatures are about 1,000 degrees warmer than we think they are today. But we have much more efficient ways of measuring in the infrared than they had. But they had the right idea, and they can see that the sunspots are noticeably cooler than the rest of the sun, which they also got hotter than we think it today. But the relative temperatures look pretty good. So they figured it out and verified what Hale had already figured out well before. For those of you who do H alpha imaging of the sun, these two images are the very first hydrogen alpha images ever made of the sun. Hale had studied the sun at Yerkes and in his own observatory before that at Kenwood in hydrogen, beta, gamma, delta, which is all in the blue and violet, and calcium in the blue and violet. And they didn't have photographic emulsions that could handle the deep red color of hydrogen alpha. But Ferdinand Ellerman was a photographer, and he worked with the companies that made the photographic emulsions, and they finally derived an emulsion that could handle the deep red color of hydrogen alpha. And at the Snow Solar Telescope, Hale used his invention of the spectroheliograph, which moves a spectroscopic slit across the image, or moves the image across the slit. And that's why there are artifacts in these images that are caused by the uneven motion of the slit across the image. But there's a great deal of detail in these images, far more than you see in the blue and calcium or hydrogen, beta, gamma, delta observations. And this immediately caught Hale's attention, and he shifted all of their work to hydrogen alpha. But Hale was a physicist, and he was well read in physics. And up in the library at the monastery, Hale's library and the open library in the monastery, there is a book which I spotted as soon as I went up there by Bjorn Brooknes in the early 1900s. He was one of the founders of dynamic meteorology, studying the motion and dynamics of the Earth's atmosphere. And Hale had that book and had read it and was familiar with the physics of vortices. And he saw things in his infrared images of the sun that reminded him of the vortices that Brooknes was talking about in his meteorology books. And he also saw patterns that reminded him of magnetic fields, like the distribution of iron filings around a magnet. So he was immediately motivated to look for magnetic fields. Now, it turns out the patterns he saw and identified with maybe magnetic fields weren't really magnetic in origin, but that's beside the point. Thing is, these motivated him to say, I'm going to look for magnetism, and he saw it. And eventually, 1908, using the 60-foot solar tower, excuse me, he was able to demonstrate with Zeeman splitting in the spectrum that they calibrated in the laboratory that there were magnetic fields in the sunspots. And by 1913, he thought he had seen the magnetic field of the sun outside of sunspots. It's the general magnetic field of the sun. Now, the opinions are split on whether or not he might have overemphasized his data and was dreaming a little bit because he really wanted to do it. I think most people now think that the magnetic field wasn't really nailed down until Horace and Harold Babcock set up their magnetometer on the 150-foot solar tower in the early 1950s and mapped the magnetic field of the sun. So this is the first discovery of a magnetic field off the Earth. the first discovery of magnetic fields, obviously, in the sun. And we now know that magnetic fields are intimately connected with the physics of and evolution of stars as well as of the sun. And although they didn't know it at the time, there's another phenomenon they discovered, the Ellerman Bomb, which is really quite a fascinating thing that's magnetic in origin, but they didn't know that. Ellerman was doing spectroscopy, and as he describes here, he noticed something peculiar about the spectrum, a sudden brightening in the spectrum. It didn't make any sense to him, and he thought, the first time he saw it, that just can't be happening. Something's wrong. But then he saw it again and decided, okay, it's happening, and I'm going to start looking for them, and he did. And this is a plate that he published in that paper that demonstrates what he saw. If you look at the A, B, and C plots, these are spectra. So remember that what you're looking at along the horizontal direction, you're looking at a change in the wavelength. So you're plotting wavelength or frequency. Wavelength is what astronomers would talk about in the horizontal direction. And if you move in the vertical direction, you're moving along the slit of the spectrometer. So you're actually changing your location on the surface of the sun. So it's a spectrum. And you notice that big dark line down the middle, that's a hydrogen absorption line. And in the A, B, and C plots, the brightening, those bright spots on either side of the line are what Ellerman was looking at that surprised him. In the D plot, you see what he was actually looking for, bright spots in the hydrogen line, which means that at those spatial locations along the slit, those points on the surface of the sun, hydrogen, for whatever reason, was now being seen in emission instead of in absorption. That's what he was looking for. What he was surprised by was this brightening that does not cross the line, which means you're not really seeing hydrogen in emission because it would go across the line. You're seeing something else that he didn't understand, and nobody did at the time. But he called them hydrogen bombs because he knew they were associated with the hydrogen line. We now know that Ellerman bombs, which are also a topic of current discussion in astrophysics papers, Ellerman, you can find Ellerman bomb in the titles of papers published very recently. This is a paper, I think, from 2012. I can't read it because the talking heads of Zoom cover up part of my slide, such as life, are a phenomenon generated by what we call magnetic reconnection, where magnetic fields slam into each other. The magnetic field lines change the way they connect, release a lot of energy from the field into the plasma. And in 1917, nobody knew what a plasma was. The word didn't even exist, probably. And you get a burst of energy, and that's what the Ellerman bomb is. And this mechanism is what's fundamental to generating flares and coronal mass injections on the sun. So really, an Ellerman bomb is like a really tiny flare, tiny flare caused by magnetic reconnection. So this discovery of elements is a topic of current discussion in solar physics. So these two images kind of bring us up to date. These are modern images from the 150-foot solar tower. The magnetogram on the right shows the Babcock's instrument, or its descendant, how it can map the magnetic field across the surface of the sun and the general magnetic field. The really interesting diagram, though, is the one over on the left, which is a Dopplergram, where the dark spots on the surface of the sun are moving towards you and the bright spots are moving away from you. And these two images are simultaneous. So you can actually compare the convection with the magnetic fields. But if you look at the Dopplergram in detail, you realize what you appear to be seeing are waves traveling across the surface of the sun with a period of about 5 minutes. And this was really interesting. Nobody had thought about that before, that there were all these waves flowing around on the surface of the sun. And this was published by Leighton, Noyes, and Simon in 3 papers in the 1960s, the first discovery. And then in 1970, Roger Ulrich from UCLA, who was a principal observer on the 150-foot tower for a long time, he published the correct theoretical description and realized that he was seeing the surface expression of acoustic waves that run through the sun. They're seismic waves, just like seismic waves on the Earth. And just as geological seismologists on the Earth can use those waves to diagnose the interior structure of the Earth, you can diagnose the interior structure of the sun in real time, which is impossible to do with light, electromagnetic radiation of any kind. Only the acoustic waves will let you do that. You can diagnose the interior structure of the sun in real time right now as using seismic tomography in exactly the same way geologists do it for the Earth. Hence, the science is called helioseismology. And then when you apply that to other stars, then it becomes asteroseismology. And these are both very cutting edge topics in solar and stellar physics now, very exciting, with lots of papers being written about them. Was discovered using the 60-foot tower and later using the 150-foot, but the discoveries made with the 60-foot tower at Mount Wilson. So the really important takeaway from this is that helioseismology and asteroseismology and the role of magnetic fields in the sun and stars are both discoveries made at Mount Wilson, studying the sun. They're both very fundamental to solar and stellar physics, and they're both cutting edge topics today. There are so many discoveries at the observatory that weren't just like a flash in the pan, oh, we saw this thing and we're happy about it, but you're actually establishing the foundations of the science of astrophysics and cosmology, really, as they will be for the next centuries. You're really establishing the science and its methodology, not just like discovered a new species or something. And just to bring you up to date on that, this is the latest and greatest in solar imagery from the new largest telescope, solar telescope in the world, which just saw first light last fall. It's brand new, the DKIS, the Daniel K. Inouye Solar Telescope in Haleakala, which has a 4-meter primary mirror, which focuses the sunlight into an image with 13 kilowatts of thermal power in it, which will melt, vaporize, and destroy anything you stick in its way. And so they put that light onto a water-cooled beam stop that only lets a tiny amount of it through that they then have to break up and filter to get to their instruments. The smallest details you see on this image, about 12 miles across, and it's only a little bit bigger, maybe 1.5 times the size of the Earth. So the planet Earth itself is a little bit smaller than the size of the sunspot penumbra. So this is a scientific program that's just carrying on the observations that were originally made and started at Mount Wilson Observatory. It's a descendant scientific program from Mount Wilson. Now I want to talk about a bunch of things that are not famous, and most people don't know about, and probably only astronomers and physicists know about. As you may remember, I said before that at the dawn of the 20th century, you really only knew the distance to about 60 stars. And if you want to understand stars, clusters, or galaxies, or anything else, you really need to know the distance. The distance is the holy grail to everything. You've got to know how far away things are. And, excuse me. So Walter Adams, using the 60-inch telescope, discovered a way to do that using the Hertz-Sprung-Russell diagram. And there's the method is outlined over here. You fine-tune your spectral type. There's a definition over there on the right-hand diagram, which is very coarse. You can do a lot more fine-tuning than that. And when you figure out the spectral class just by counting the lines, then you can draw a vertical line, like the vertical white line over on the HR diagram on the spectral type. The purple curves are what they call luminosity class for giants, main sequence dwarfs. You can get that by looking at the shape and width of the spectral lines themselves, not just counting them, but actually looking at the details of the line. And so you figure out what luminosity class you are. That tells you what purple curve. You go to where that purple curve crosses your vertical line and draw a horizontal line like I've done for the sun. And you get the absolute magnitude, which means the true brightness of the star. For the sun, it's about 4.8. Well, you know now its absolute magnitude, you know its apparent magnitude because you're looking at them, and the handy dandy formula up there on the upper left tells you how to get a distance in parsecs. So you can use the spectrum to get a distance. And so doing that at Mount Wilson and a bunch of other observatories, the number of stars people knew the distance to expanded very rapidly. There were also trigonometric parallax programs carried on at Mount Wilson photographically that expanded that number too, which you can see an explosion in the number of known stellar distances in the first 3 decades of the 1900s, in large part due to the spectroscopic redshift method discovered by Walter Adams on the 60-inch telescope. While he was doing that, he noticed that the red M-class stars, the absolute magnitudes, they were all either very low, very dim, or very bright, and there were none in between. And he recognized that this meant that there were dwarf stars and giant stars. So if you just look at a star and it looks red, unless you look at it carefully, you don't know if it's a red giant far away or a red dwarf up close. You can't tell the difference. So you look at the spectrum and then realize, oh, that's a red giant, so it must be far away, and it's a red dwarf, must be close. So we talk about red dwarf and red giant stars routinely in astronomy, but the difference between them was discovered by Walter Adams while he was doing his spectroscopic redshift project. Another very important first at Mount Wilson was astronomical interferometry. Albert Michelson had done optical interferometry in the laboratory to study the speed of light. And he had used interferometry at Lick to measure the angular diameters of the moons of Jupiter. And he wanted to try it on stars. And he came to Mount Wilson. Hale said, yeah, go for it. And he and Francis Pease put together this 20-foot beam. A diagram on the upper right shows the light path, how it works to the North Cassegrain focus. And they used it to derive the angular diameter first of Betelgeuse, which they got right. They get about a 0.047 arc seconds, which is not significantly different from the number that you would get if you used a modern interferometer to do it. If you know the distance to a star and you can measure its angular diameter, then you can convert that into a linear diameter. And now that tells you a lot about the physics of the star, its surface brightness, surface emissions. Knowing the distance and size of something is really critical. Exactly how they did it, their observing technique is kind of opaque in the Astrophysical Journal paper, but they published another paper in the Proceedings of the National Academy of Sciences at the same time, where their description of what they were doing is easier to read and follow. And basically they had 2 images, but the images were covered up by interference fringes, one set of which will not change as you move the mirror and another set that will. So you have constructive interference. So you move the outer mirrors on the interferometer until you get destructive interference and get rid of the interference fringes. And when you do that, the separation of the outer mirrors corresponds to the angular diameter of the star you're looking at. And they proceeded to measure a large number of stellar angular diameters. This again is very cutting edge astronomy, and I'll show an example of that later on. But it's a whole new field of astronomy and astrophysics, is astronomical interferometry, that was started at Mount Wilson Observatory. Even before the radio interferometers got into it, they were doing optical interferometry. And with the success of the 20-foot, they tried to build a 50-foot. And there's Francis Pease looking through it. But one of George Ellery Hale's many habits was to push every technology he encountered all the way to the breaking point. And he wouldn't give up on it until it literally broke and failed. And so this technology basically drove the construction, the interferometry technology, to its breaking point.
They're just really hardcore at it. Yeah.
Can you silence your microphone, please? Thank you. They pushed this to the breaking point that the flexure in the system was so much that they could only make one proper observation, and then they just couldn't use it anymore because they had to wait for better construction techniques, more rigid materials. But they did push the envelope. Now, I also said that Hale wanted to do infrared astronomy, and he knew that early on. And that's one of the reasons he wanted to switch from refractors to reflectors. He tried to measure the temperature of stars in the infrared at Yerkes Observatory, and it didn't quite work. They detected the stars, but Hale and Nichols were not willing to say they'd actually measure the temperature because their data was too noisy. But Seth Nicholson and Edison Pettit started to work on the world's first consistent, steady program of infrared observing using the 100-inch telescope and again a thermocouple at the focus. And I think they were using the Cassegrain. I'm not sure which focus they used. And they looked at the planets, they looked at the moon, they looked at stars, and it's particularly interesting that they found the night side of Venus just as hot as the day side of Venus, which surprised everyone. Everybody thought it was a nice cloudy day, cool surface on Venus, and Nicholson and Pettit disabused everybody of that notion. So they started the infrared ball rolling, if you will. The very first all-sky infrared survey ever done was done at Mount Wilson Observatory using a custom-built telescope that's pictured here. It's currently at the Udvar Hazy Center at the Space Science Exhibition, on exhibition there. It was custom-built, and I find it really interesting that what they call chopping is a standard technique in astronomy for bouncing your source between two detectors, so you can take out a bias that's caused by any one detector or take out whatever else you want to get rid of. These guys actually vibrated the entire primary mirror back and forth of 20 hertz and then only amplified the 20 hertz signal so they could select point sources and get rid of the non-varying background. They were looking for a catalog of point sources. And so they built the very first. The 2 Micron Sky Survey, finished and cataloged in 1969, not to be confused with 2MASS, the 2 Micron All Sky Survey, which was done much later, around 1997 to 2000, something like that, and spread out around the world. This was roughly the same wavelengths, up to 2 microns, but much earlier and with much older equipment. But it was the first foray into infrared survey. And because Mount Wilson, with this project and earlier infrared survey, were so successful, infrared astronomy really took off because of the work being done in the infrared at Mount Wilson. And so that's an entirely new discipline of astronomy in the infrared that was started at Mount Wilson. And of particular interest, a follow-up to that survey using the regular 60-inch telescope, looking at the Orion Nebula, discovered the infrared counterpart of the Orion Nebula, which is called the Kleiman Low Nebula, which itself is interesting because it demonstrates all the dust and gas that's present that you can see optically, really, in the Orion Nebula. But of much more interest, to me anyway, is what's called the Becklin Neugebauer object, which was discovered with the 60-inch telescope in the infrared. You can see it on the infrared image here, the upper image, taken from the European Southern Observatory, very large telescope, where the BN, notice, labels this very bright spot. And there's the image on the lower left. It's hard to see, but there are a couple little black lines and indicating where the Becklin Neugebauer object is, and it's invisible. Invisible light, you can't see it at all. You'd never know it was there. Visible only in the infrared. And this is the very first protostar still embedded in its original dust cloud ever discovered. And it's basically a holy grail of astronomy. You think you know how stars form, but you can't see them doing it because they're buried in the dust cloud and they're visible only in the infrared. Well, it's soon realized that the Becklin Neugebauer object is one of those stars. And so it's a very exciting discovery. And Eric Becklin, who was a co-discoverer, is still around, works for SOFIA. And I've talked to him about giving a talk sometime to the Mount Wilson lecture series on discovering the Becklin Neugebauer object. And if you're really interested, you might be able to get in touch with him and get a BN talk. He's a really interesting guy. And so this is really a big deal in the infrared astronomy business. Now, you're all familiar with Sirius and its white dwarf companion, Sirius B, which is the little tiny thing dot on the lower left. The reason I show this is that very early on, astronomers knew from the spectrum, and you can see the temperature of Sirius B compared to the temperature of Sirius here, that white dwarf stars were very hot. But if you just see a white dwarf star floating around out in space, you know it's very hot from the spectrum. But since you don't know how far away it is, you don't know how big it is, you don't know if it's a giant or a dwarf or what's going on, you only know that it's hot. But Sirius B is a companion of Sirius, which is very close. We know where Sirius is, which means we know where Sirius B is. We know the distance. It's very hot, but it's also very dim. And if it's that close, it cannot be very dim unless it is really small, which means it has to be about the size of the Earth to be that dim at that temperature. But it also orbits Sirius B, which means you can get a mass for it from the orbit. So now you know that it's got the mass of the sun and the size of the Earth, which is very weird and is extremely dense. And so Arthur Eddington put all this together and said, wow, this must be really dense, really weird, and with a very high surface gravitational redshift. So remember that Eddington is famous for going out in 1919, observing the total solar eclipse, watching the positions of the stars move, and demonstrating the curvature of space as predicted by Einstein's general theory of relativity. And it was a really big deal at the time. Yeah, some modern analysts think that he might have overemphasized his data a bit too, but it's famous now for that anyway. So when Eddington published his prediction of what the gravitational redshift should look like in 1924, Walter Adams observed Sirius B with the 100-inch Coude spectroscope and measured spectroscopically the gravitational redshift from the surface of Sirius B and got the same number that Eddington had predicted. So he observationally verified the prediction for the gravitational redshift. This nails down the fact that red or white dwarf stars are incredibly dense. They're too dense, and therefore they're made out of some weird stuff, not normal matter, because you can't make normal matter that dense. And indeed, we now know they're made out of what's called degenerate matter, which is a whole nother talk that has different thermal properties and doesn't act the same as regular matter. But another interesting thing about this is that it's fairly easy to comprehend the curvature of space by drawing some kind of surface and making a 2D analog. The curvature of time, on the other hand, is really hard to wrap your head around. And in fact, the measurement of the gravitational redshift is a measurement of the curvature of time. And you would plot a time curve by measuring the gravitational redshift as a function of distance from the surface. Here, you're only measuring one, you're measuring the surface. So by itself, it's not really a measure of the curvature of time, but it's the fundamental measurement you use to get the curvature of time. And so this is the very first gravitational redshift measurement ever made that I know of on or off the Earth. Now we can do it not quite routinely because it's still hard to do. And in this case, it was very hard to do, as Adams tells in his paper, because he has to make sure light from Sirius A isn't bleeding into his spectrum of Sirius B. This is a fundamental verification of general relativity that nobody ever talks about. They only talk about Eddington and his eclipse variations, observations in 1919. This is a completely independent verification of general relativity by looking at the gravitational redshift. There's also the mysterious element nebulium, beginning with William Huggins in 1864, looking at planetary nebulae and trying to figure out what they were. He identified a number of spectral lines that were not corresponded to any element that anybody knew. So they invented a new element, called it nebulium. I mean, everybody knew that hydrogen had first been discovered as an unidentified spectral line in the spectrum of the sun. And so nobody was terribly surprised that there should be a new element. But then they got worried because from the spectrum, they could figure out its atomic configuration and realized it looks funny. It should be a low atomic weight element. We know them all. There isn't room for a new one. So what's that? Nebulium became very mysterious. And in 1927 and 1928, Ira Bowen, who was a spectroscopist at Caltech and Mount Wilson Observatory, did the theoretical calculations and realized that nebulium didn't exist. People were seeing ionized oxygen and nitrogen, doubly and singly ionized. And so he was able to identify the unidentified lines. He got rid of nebulium and realized that we were looking at ionization states. So astronomical observations can either show you something new in the periodic table or show you that you were wrong when you first thought there was a new element. The difference between nova and supernova was determined first by Bode and Zwicky, who were both Carnegie and Mount Wilson astronomers. Whether they did their observations at Mount Wilson, I doubt, because nova and supernova, some of them they probably did. Just like Adams and his red giants and red dwarfs, they realized that there were two different classes of nova, the super ones and the normal ones, with nothing in between. And so the difference between nova and supernova were first discovered by astronomers at Mount Wilson Observatory. This is a picture of T Tauri, the prototype star for T Tauri variable stars and Hines Nebula. And the reason I put this up here is because the T Tauri class of variable stars was first determined by Alfred Joy. He used about 30 years worth of observations from the 60-inch and the 100-inch telescopes and realized, putting them all together, that this is a new class of variable star people didn't know about before. He cataloged all the things they have in common, identified all of the T Tauri class variable stars. We now know that T Tauri stars are stars late in the formation of pre-main sequence evolution. They have not yet become main sequence stars. They're all still associated with the clouds of dust and gas they were originally born with, but they're not quite main sequence yet. So they fill a gap in your picture of stellar evolution. And this, remember, is the problem that George Ellery Hale was really interested in the first place, was stellar evolution. There was a lot back then they didn't know, and a lot they didn't know in Alfred Joy's time, but they filled a gap in that story by identifying the T Tauri class of variable stars. And another really interesting one is technetium. Charlotte Moore thought she could identify technetium in the spectrum of the sun, but noticed that it was right on top of a molybdenum line. And today, nobody thinks there's technetium in the solar spectrum. It's just a misidentification, probably, of the molybdenum line. But Paul Merrill, using observations from the 60-inch, the 100-inch, and the 200-inch telescope, realized that there was technetium in the spectrum of a certain class of red giant stars. And he pointed out technetium, until then at least, was a completely artificial element created only in the laboratory, not seen in nature anywhere, with a short radioactive half-life, and therefore you should never see technetium in the spectrum of a star, but you do. And so you have to explain that. Maybe there's a stable isotope. No, there isn't. Or maybe S-type stars somehow produce technetium as they go along. And that's the key. That's one of the alternatives that Merrill pointed out. And only a year later, this is 52 and 1956, I believe, when he published it. In 1957, Burbage, Fowler, and Hoyle came out with their very famous paper in the Reviews of Modern Physics, where they finally nailed down the real science of stellar nucleosynthesis, the creation of elements in stars by nuclear physics. The very first observational clue that that's happening in stars is the observation of technetium in the spectrum of red giant stars by Paul Merrill using the 100-inch and 200-inch telescopes. He called them S-type stars. That's a spectral classification that no longer exists. They were eventually recognized as being special cases of M giant stars. So here's a summary of, that I might have padded a little bit, but don't worry, of discoveries made at Mount Wilson Observatory. And I didn't discuss Bade and his discovery of the stellar populations, which was also done at the 100-inch telescope during the 1940s in M31. There's so many firsts and so many discoveries made at Mount Wilson Observatory. You couldn't list them all on one slide. And I didn't go through all of them, I think I gave you enough to get the point across. There's a lot that the observatory is not famous for, but still fundamental and important scientific discoveries. And I do want to talk just a little bit about what it's like today. And so here I put labels on everything. And CHARA is an acronym for the Center for High Angular Resolution Astronomy at Georgia State University. And that's really the heart of big scientific research going on at Mount Wilson Observatory today. It is an optical interferometer. The one used by Michelson and Pease in 1921 was the first and therefore the largest in the world. And the 50-foot was the largest in the world. And Chara is still the largest in the world with a maximum baseline of 320 meters, 6 telescopes scattered around the mountain. And I believe they just got a new grant for a new telescope. They might put a 7th one somewhere. I'm sure they'll argue with themselves about where to put it. But they can combine the light from as many as 6 telescopes. There were only 2 mirrors on the Michelson P's interferometer, but these guys have 6. It's all computer driven and controlled now. You don't have a graduate student climbing to the top of the class, risking his life, moving mirrors back and forth. You can actually do it safely and electronically. Hal McAllister was the godfather of this array. He's now retired and running around Florida and Georgia in his RV fishing. So there are 6 1-meter telescopes. Fascinating technology. And here's an example of the kind of thing you can do. The interferometer does not make images. It makes interferograms, and you have to do a Fourier transform of the interference pattern to get an image. So you synthesize an image. This is an example of an image that's been synthesized and then smoothed with a theoretical description of the image. So this is better than what you would normally see if you just go straight from the synthetic image. But it's Regulus compared to the sun. That's a real size and shape comparison. So because they have so many telescopes, they can get not only the diameter, like the diameter of Betelgeuse that Michelson and P's got, you can get the shape. And Regulus rotates very fast. So the axis of rotation of Regulus is horizontal line drawn across this frame. The theory of rapidly rotating stars tells you that the pole should be brighter than the equator because the pole is in closer to the equator. It's squished out at the equator farther from the pole, so it should be cooler because there's much more stuff between the pole and the equator. And this instrument is able to map the distribution of brightness across the surface of a single star and show you that that theoretical prediction is in fact true. They're now putting adaptive optics on the array and hope at some point to be able to reliably get interference images of active galactic nuclei. Right now, they're doing exclusively stars, but if they can do AGN, there's a lot of people waiting in line for that. That would be really exciting. And they're working on that still. The infrared spatial interferometer isn't being used much anymore. I think a group from JPL is going to take that instrument over. But it did its observations long wavelength, 10, 12 micron window in the atmosphere. The plot on the upper right shows the ability of this instrument to monitor the expansion of circumstellar shells of warm dust around red giant stars. And they observed in a 2009 paper that the diameter of Betelgeuse had shrunk by 15% over 15 years. And of course, whenever you say anything changed on Betelgeuse, everybody jumps up and down and says, blow up already. Well, you were waiting for the big supernova. But okay, it's not going to happen that way. It's not going to give you any clues. When Betelgeuse blows up, it'll just blow up in your face and you won't see it coming. That's the way the stars work. And finally, not all of the science done is astronomy. JPL has an air pollution experiment at Mount Wilson Observatory, which looks at sunlight directly and bounced off the San Gabriel Valley to look at CO2 and monitor it. And as you can see by the plots on the bottom, if you're over in the East San Gabriel Valley area, it's not too bad. But if you're over on the west side, as the day progresses, you're getting a little more CO2 in your air. And you can thank JPL and Mount Wilson Observatory for showing you this. And this is my last slide. This is the end of my talk. And I thought, since this is a Palomar talk, the Palomar people would like to see this slide. you can tell where I'm standing on the catwalk of the 200-inch telescope. The only open house I'm familiar with at Palomar took place on June 25th. And the pre-event assumption was that a few people would show up, maybe a couple of hundred. And so they were very relaxed and very informal and very slow tours in the 200-inch. And thousands of people swarmed Palomar, about 5,000 people. If you're familiar at all with the layout, you can see how the line snakes from the stairs all the way back to the road, almost to the visitor center. I started my journey into the dome at the stairway right at the foot of the 200-inch at a time when there were not very many people and the tours were running very slowly, and it took me an hour to get up there from that point. Now you can see that if they kept the tours going at that rate, it would take 8 or 10 hours for all the people in that line to get up there. And once people realized how many had shown up for the tour, panic mode set in. They were running them through the dome as quick as they could, getting the tours done. This is Palomar and Mount Wilson are both, I think, really popular places. And if you do the work for an open house like this, you can get a lot of people showed up. I was even amazed at how many people, thousands, literally showed up at Palomar. They parked the road solid outside the observatory, and that even tempted a fire marshal to come up to the observatory and tell me, you got to watch, getting so many cars on the road, they can't get out. If there's a problem, we're going to get slammed. And I think it panicked the Palomar staff, and they've never done an open house like that again, to the best of my knowledge, 16 years ago. We ought to try it again someday. You really, it works. You guys are popular. And so that's the end of my talk. I'll turn it back over to Steve Flanders, and thank you for paying attention.
Can I point out that speaking of the open house here, Mike Burton, who I think is with us, was a docent and participated, worked at that open house. Mike, you still here?
I am.
Wow.
I think that we had half a dozen docents giving those tours. I don't remember what time the tours started, maybe 10 o'clock in the morning, and they ran till most of the people got done. And at the end, the half dozen docents who gave those tours, we looked like washed out rags. We didn't have time to eat lunch. We barely had time to take a sip of water or use the restroom.
Yeah.
But it was one hell of a lot of fun, I'll tell you that. And Tim, this was a terrific talk. I thought I knew some stuff about Mount Wilson, but I see that what I know about Mount Wilson was just really scratching the surface. Thanks for the talk. I really enjoyed it.
Well, you're welcome. And I suspect what most people think they know about Palomar is pretty much the same thing, just scratching the surface.
If I might, in the chat,
Mm-hmm.
Harlow Shapley's daughter, Deborah Shapley, has left a note. Deborah, if you are still with us,
I'm here. I came back. Here I am.
could you
Wow.
pose your questions, please?
Thank you so much for this wonderful talk. I've been out there. I live in
Well,
Washington.
thank you.
Just fantastic.
Thank you.
I'm a journalist and a historian and not a scientist nor an astronomer, but I knew
Oh, well.
my grandfather very, very well. And he was a wonderful man and witty and irreverent, as his colleagues at Mount Wilson found out.
Yeah.
So I'm aware of that. And he and Hubble, of course, had a very interesting relationship. I'm preparing
Yes.
a website called harlowshapley.com. And am working on, it will be 12 small chapters about Harlow Shapley's life and career, and some social media, and everybody's welcome to join in.
Oh,
Um,
cool.
For my question for Tim Thompson is this: here is an object that Granddaddy kept on his desk, and it's among my father's effects, of which there isn't that much. But offline we can finish this, but let me read you. You have to ask, why did Harlow Shapley keep with him an image from 1910 from the 60-inch? He didn't get there till 1914. And I'm going to read you the back of it, and then anybody who wants to get to me offline can respond. But the writing, which looks like Granddaddy's, but could be somebody else, says NGC 4565, Coma Berenices, is that right?
Yeah, Coma Berenices.
Berenices, excuse me.
Yeah.
Then it
Yeah.
says MT Wilson, 60-inch, EXP 5H, 5 hours, 1910. Then it says Radvel plus 1100 km per whatever that metric is. Distance
I'm not
7.6 times 10 to the 6. Diameter 31,000. One of the largest. So maybe this is an unusual object from 1910 that he felt a special interest in, or a gift.
Interesting. Well, it's an edge-on spiral galaxy, and of course Harlow didn't believe that they were outside the Milky Way
Right.
until Hubble kind of forced him into it, which made Hubble very happy. And so I'll tell you, I've met Mildred Shapley
great.
once.
My aunt, yeah, she's
when
great.
she came to the Carnegie Open House. Yeah, so several years ago.
Yeah.
She and Don Nicholson were old friends, and she came looking for Don, and we sat them down next to the solar telescope. And so she sat down and she said, "Oh, I only came here to see if this old guy was still around."
Mildred was great.
Yeah, she was great. I enjoyed spending some time with her and Don together. So I have no idea why he would have kept that image,
but he did
somebody
at
else might.
1917, I think, see a nebula that he decided was far away and outside the galaxy, and published something finding that, and then decided to go another way and give up on the external galaxies. So there is a 1917 paper, which might be a 1916 observation.
Yeah.
Anyway, we don't need to get into all of that, but I will send you the data about this photo in case somebody has a clue.
Okay.
Thanks.
Okay. Thank you.
Thank you, Tim. Also from Germany. You may remember me when I was visiting LA in 2018, moving around with some guys from the Los Angeles Astronomical Society.
Oh, okay. Good. I can't remember.
I also met you there.
Oh, good. Good. I hope I made an impression.
Yeah, sure. So I recognized when I saw your bird today. So, bye. Thank you so much.
You're welcome. Thank you. I forgot to shave this morning,
No problem.
Well, can we briefly open things up for a couple questions? Are there things people would like to ask? We've had a long session, so I want to kind of bring it toward a close. But if there are other questions, please turn on your mic and we can ask.
I was there 4 years ago, and then I left.
Anything else?
I'm Tim, you mentioned the 4-meter telescope on Haleakala. Is
Yeah.
that different? Is that different from the Amos 3.67 meter?
I'm not familiar with the Amos telescope. The largest in the world until DKIST opened up was the telescope at Big Bear Solar Observatory. And I forget its aperture at the moment. But right now the 4-meter at DKIST is the largest, and I'm not familiar with the Amos telescope, so I can't say anything about that.
I think that I earlier saw Tom Spirach attending this talk, and he can tell, he worked at Big Bear Solar Observatory. I don't know if he's still on the line. I see a number of people. You had, I think, over 150. Now people, it's only 90. But Tom Spirach, are you still on the line?
Yes, hello, I'm here.
What's the aperture of the telescope at Big Bear, which is called the Phil Goody telescope?
Yeah.
It's I believe it's 1.6 meters.
And Tom, I have another
Yes.
question for Tom. Tom, would you describe the work that's been done about the magnetic properties of the sun at Big Bear? Is that kind of the child of George Ellery Hale's work at Mount Wilson?
Well, I think kind of by definition, all magnetic work on the sun is a child of Hale.
Yeah.
Kind of by also, all solar work nowadays needs to be coordinated with its own magnetic images. So whenever you take images of the photosphere, it's always desirable to have the equivalent magnetic images of that particular area on the sun at that particular time, because the magnetic field drives all the activity.
Yeah, you want to be able to correlate a magnetic object with a visible object. The sunspots is particularly important to do. The Big Bear was the brainchild of Hal Zirin at Caltech. And not everybody at Cal liked Hal Zirin all that much. And the Caltech astronomers were really much more interested in Palomar and cosmological observing. So once Hal left, they divested themselves of Big Bear, and it's now, and the New Jersey Institute of Technology actually runs the Big Bear Observatory. And the Goody telescope, to the best of my knowledge, was the largest solar telescope aperture in the world before DKIST.
Well, are there other questions?
I bamboozled them, the whole crowd.
I can ask a question if I can.
Sure. Sure.
Great talk. Thank you so much, sir. And this was wonderful.
Thank you.
I'm not an astronomer. I think I'm an amateur astronomer. I'm an architect by profession, but I think what strikes me is the like what you said about the shift from the refractor telescopes to the reflectors. And I'm curious, like if for like laymen like me, amateur astronomers, if collimation is not an issue, once collimation is set up, is a reflector better or a refractor better? And that's my first question. Second question is that the Hubble Space Telescope is a reflector? Is that correct?
Yes.
And is that the same reason why it's a reflector, like because of the shift from the refractor anatomy to the reflector being easier? Is that the same reason?
Okay, so your first question, I'm not sure what you mean by whether the refractor or reflector is better when they're collimated. It depends on what you're trying to look at. Amateur astronomers, for instance, know very well that for moderate apertures, like up to say 8 inches or something, because nobody can afford a bigger refractor unless you make it yourself, like Jeff Schroeder did, made his own 11-inch refractor. The refractors give you much better definition and image quality when you're looking at the planets, for instance, than a reflector will. So if you want to do planetary imaging or astro imaging of extended objects without a huge aperture, you're probably better off using a refractor like a Takahashi or something than you are a reflector. But the key really is aperture. Hale pointed out in 1897 that around 1.5 meters, at least on the ground, is as big as you can make a refractor. And the reason is that if you point the telescope up, the refractor lens will sag under its own weight and change the optical characteristics of the telescope. So at some point, it just is no longer worth trying to do. You have to transition to reflectors. And of course, the opacity of the lens to infrared. And so if you're talking about the Hubble Space Telescope, why is it a reflector? Well, one reason is from space, you can see wavelengths that are invisible on the ground, ultraviolet, infrared, that will not travel through glass. So you have to have a reflector in order to use those wavelengths that will not pass through the glass. And secondly, it's expensive. If you tried to make, like the Hubble Space Telescope is basically 1.5 meters. It's about the same size as the 100-inch mirror. Or it's 2.5 meters, about the same size as the 100-inch mirror, slightly smaller. If you tried to make an objective lens 2.5 meters across, you'd be spending a large chunk of the national debt. That's incredibly difficult to do and thoroughly impractical. And so the Hubble Space Telescope is a reflector primarily because the wavelength coverage, you don't want to put an opaque filter in the front of it, but also just because it would be a lot cheaper to make it a reflector than it would a refractor.
That's
Hope that
amazing.
answered
Thank
your
you.
question.
No, that's
Yeah.
great. Thank you so much.
Good.
Hey, Tim.
Yeah.
Gio here. I don't know if you remember
Hey,
me.
Gio. Yeah, I remember you. What's up?
So I just wanted to add one thing, since I happen to have the most view-through refractor behind me at the moment. That's the most view-through refractor on planet Earth. Refractors are great.
Yeah.
They're wonderful. But when you look at the moon, you see a purple outline around the edge of the moon. When you look at Mars, you get that same purple outline. So I love refractors, but you want to get the true image, you definitely want to have a mirror and not a lens.
Well, unless you've got a shot-on media like mine behind me here, in which case you don't get the purple halo.
Yeah, remember that George Hale's one of the problems he had with the 40-inch at Yerkes was spectroscopy. He had to image each line individually because of chromatic aberration. The solar tower telescopes, the 60-foot and 150-foot, are refractors. They have lenses at the top, but they're super long focal ratio, like the 150-foot tower is an f150 refractor. And if you make a really long focal ratio, you can inhibit chromatic aberration so that it's not such a big deal. And you can also do it with a multiple element lens, a triple element instead of a double element. And it is a triple at the 150-foot tower. So there are ways around it, but the easiest way is to just get a reflector, especially if you want large aperture.
So I have a comment about the mapping of the Milky Way, and I don't mean to take anything away from Harlow Shapley, but Didn't William Herschel map the shape of the Milky Way in the late 19th century?
William Herschel tried to map the Milky Way in the 1780s, 1790s.
Yeah.
And he was unable to do it. So he drew a picture, but it really didn't amount to much. Herschel's method was to point his telescope and count the number of stars. And then he pointed it all over the sky and counted the number of stars. And he figured that if the Milky Way were, a flat disk type thing, he would see more stars in his telescope tube that way than he would if he went that way. And he was looking for a difference in the distribution of stars around him that would give him a clue as to the shape. But his telescope wasn't powerful enough, and everywhere he looked, basically he counted the same number of stars on average, and he had to finally just give up and pretty much assume that there's stars, all the way out in every direction. So he tried, but he was unable to do it. And of course, the idea of other galaxies that Hubble discovered and extragalactic systems goes back philosophically all the way to Immanuel Kant, who had this island universe hypothesis when he was looking at spiral nebula. But it was a philosophical guess. It was just him saying it ought to be that way and therefore it is. And there's a big difference between that and saying I just measured a distance to it, therefore it is.
So I guess that's the difference between a philosopher and an astronomer.
Yes, I started out as a philosophy major and I'm not, and that's why.
Well, we are going on 2 hours, and I think we are taking up. Timothy has been very gracious with the time that he has given to this, but I think we probably need to start winding down. Tim, could I kind of close off with kind of a very general question? What do you think? What do you know is in the future? What is the future for Mount Wilson Observatory and Mount Wilson Institute?
Well, we, well, at least I, and I think it's fair to say we, would certainly like to see the big telescopes get back into research astronomy in a way they have been unable to because of light pollution, of course, from the city. Chara Array makes most of its observations in the near infrared, where light pollution doesn't exist. So you could put it, well, you wouldn't want to put it in downtown Los Angeles, but in general, the light pollution is not a problem with those wavelengths. And there is a large community of universities, community colleges, even high schools, a whole lot of schools in the LA area that have no access to astronomical facilities, or they have very poor ones on campus perhaps. And Mount Wilson could fill that bill. And I've talked with a few others about a consortium of schools that would get together and operate their own business and rent time on the telescopes and do certainly university grade research, like master's thesis, undergraduate thesis, or even doctoral work for that matter, in the infrared for Mount Wilson, where the light pollution is no longer an issue. Of course, we need instruments to do that, and we're kind of poking in that direction now with some imaging instruments, a spectrometers, what you really want. And you need grants to do that. And in order to get grants, you need to convince somebody that you know what you're doing and you won't pour all their grant money down the drain. And so we start with a little and work our way up and bootstrap. And eventually, I think we can work our way into that. And of course, we want to maintain our program of public astronomy. And there are ways to do that using the Cassegrain focuses on the 100-inch, for instance, a lot easier than trying to do Coude focus. So the pointing back towards research, at least, is what I think is the primary goal for the future. But we have a lot of programs going on now, like the lecture programs and the concert programs, when people can get back to the observatory, partly because of the virus and partly because of the fire, that we want to keep going. We don't want to cancel those and stop doing them for whatever reason. Those are good programs. We want to keep those programs alive. And that's the way I see it. So I don't know if any of my bosses are listening in or not, but that's the way I see it.
Well, we certainly hope Mount Wilson can take that direction. I think that would be a wonderful thing for everybody. Timothy,
Yeah.
well, thank you very much. That was a wonderful presentation.
Thank you. And thank you to all those people in chat who said I did a good job. I appreciate it.
And the video will be on the Palomar Observatory YouTube channel, probably in a couple of days. And with that, our next Greenway presentation is in 3 weeks, February 27th. Dr. Rahib Gangule of the University of Michigan will talk about black holes and gravitational waves in a talk called A Journey from the Edge of Darkness. Again, that's in 3 weeks. And with that, I want to thank everybody for coming. I think it was a great session. I appreciate everybody's participation. And with that, I'm going to end the meeting and thank you all for coming.
Okay.
Bye-bye.
Thank you, everybody, for listening.
Great talk.
Great talk.